what we're going to look at today is we're going to start talking about something called a line integral. So the line integral is essentially, so when we were doing integration in a single variable, you actually imagine that you would integrate over a line segment on the x-axis. So you had a function of x, and then you integrated over a line segment on the x-axis. And so, basically what we do is we break it up into little delta x's. So we break up a lot of little delta x's, and then, you make the delta x's really small, and then that would end up giving you the entirety of the area. So what we're going to do now is we're going to say, well, what if instead of just having to integrate on along the y-axis, or excuse me, along the x-axis, what if I had a curve of any kind, right? So a curve that was not necessarily say, for example, a well-defined function. So it was a curve in space along the xy plane, right? It went all over the place, or it was in the xyz plane, so it was three-dimensional, or we could even imagine it if in more than 3 dimensions, okay? What do we do then? How do I go about doing that? And the reason why we ask this question is because sometimes it's really, really very handy. So say for example, you're doing something in, you're doing an application in which your function is dependent upon some kind of time t. So we have a function dependent upon some kind of time t, okay? And, but it's not constant. It's not constant like it would be if it was on the, if we imagine the x-axis being the t-axis, right? But instead, t changed depending upon our values of x and y. So we had parametrizations for x of t, and we had a parametrization of y of t, and so our value for the function depended upon where it was in the xy plane instead of just along that x-axis. And say we wanted to do something with it where we were like, okay, depending upon where it is located on that xy plane, okay, we get a different value for whatever quantity we're looking at. Say maybe its density, or we might look at it and say, okay, well, what about its charge or its current at this particular time t, right? But that time t is not consistent, okay, or the same, in a very linear way as if it would be if it was on that x-axis. So what this is going to allow us to do is it's going to allow us to work with a lot of different kinds of functions. It'll allow us to kind of simplify the mathematics for working with more advanced properties, and to work with things where, say for example, where time is not perfectly linear, okay, but instead is actually something that is shifting and changing as our particle moves through a path in the xy plane or the xyz volume. All right, so now let's look at, we're going to little line integrals. So let's start out with the basic concept here. So let's imagine I have a curve. So here's my curve. My curve is in space, okay? And I'm not integrating, I'm not looking for the area under this curve. That's not what I'm looking for. Instead, what I have, okay, and by the way, this curve is parametrized. It's x equals x of t, okay, and y equals y of t, all right? And then we're told, say for example, t is greater than or equal to 0, less than or equal to, or a, t goes from a to b, whatever that is. And then what we're going to do is we're going to evaluate, we've got rho of xy, and that's some function for something, whatever it is, all right? And we want to figure out, right, we want to find the integral for rho of xy along this path, right? What is the integral for rho of xy along the path? Okay, so what I'm going to do here in order to do that, right, is I'm going to say, okay, well, let's imagine that I've got I'm going to break this up. So S is the arc length, whatever that arc length happens to be. It's actually a function, right? We've done that before in second semester calculus. And I break it up into delta S's, okay? Now here's the thing about delta S's. Right, so this is delta S1, here's delta S2, here's delta S3, right? So these are arc lengths, and we're going to break them up. And it turns out that we don't, or this is delta Sn, or delta Si. We don't actually have to have them all be the same length. It doesn't matter if they're all the same length, okay? That's fine. Now what we do is we're going to find within this region, we're going to have rho of, call it xi well, let's go to the I one. We're going to have like rho of xi star, yi star. Okay? All right? And so that's going to be like, that's the value of our function. Remember the thing that we're looking to integrate? Okay? Wherever it's located upon that path. Okay? So whatever value it is in the xy plane, that's going to be actually the value of our function, right? And so if we think about this, like an approximation, right, for its integral in that place, okay? So just like an approximation there would be rho of xi star, yi star, okay? And that's actually an approximation, not necessarily of its area, but actually of its line integral, all right, times delta si, okay? That's approximately equal to the line integral in that region. All right, you've seen this before. You know that this is just some value for the function over an arbitrarily sized region or piece of the curve. So what we're going to do is we're actually going to like go in, we'll sum up all of those. Okay, we're going to get the sum of rho of xi star, yi star, right, times delta si. And we're going to go I equals 1 up to n. And then what we'll do is we're going to say, okay, cool, that's great. But like now what we want to do is we want to make each one of those regions to be smaller and smaller and smaller and smaller. Okay, that's kind of the idea that we do when we go through and we integrate something. And so consequently, our integral on C, and C is called the curve. This is the curve in space. And that's how we denote it. It's kind of like when we had the double integral over R, or we had the triple integral over D. It's the same idea. The integral over C of the curve in space of f of xy ds, right? And we'll talk a bit more about ds. But ds is going to equal the limit now as n goes to infinity of this sum, I equals 1 up to n, rho of xi star yi star times delta si. All right, so it's an integral. The difference here, right, it's like basically we're just summing up each one of these regions just like we've done before. The difference here is we're doing it over ds, and ds is the change in the arc length. So this is going to be a change in the arc length. We've actually seen this before in our work with arc lengths just before. We've done this before, in terms of arc lengths, so we can kind of work with this. But that's going to end up being our integral, and that's kind of the basic idea that we have for finding the value of the line integral. Okay? So let's take a look at some examples here, because I think that's going to kind of help us out. Before we look at some examples, let's actually think about what is that ds? Okay, so ds, and that is the change in our arc length. And if you remember, okay, that the length of our curve L, okay, is going to equal this the integral from a to b of the square root of dx dt squared plus dy dt squared, okay, and then dt. All right, so basically what we've done in order to find our arc length, we actually integrated all of this. And what is this? Well, if x equals x of t and y equals y of t, right, for t greater than or equal to 0, less than or equal to t greater than or equal to a, less than or equal to b, then what this is, that's ds. So ds is going to end up equaling the square root of dx dt squared plus dy dt squared, okay, dt. And that's just kind of like reviewing what we had before from, say, for example, your second semester calculus course, where you actually had to go out and find the arc length of curves. What we're going to do here is we're actually just going to take this as our ds, and we're going to adjoin it to our equation. All right, so what we end up with here, right, we can define that the integral from along a curve C of f of xy ds is just going to equal the integral along that curve from a to b, okay, of f of x of t, y of t, okay, times the square root of dx dt squared plus dy dt squared. So now what we've done is we've gone and we've taken our parametrization and we've utilized that parametrization in order to transform our function of x and y into basically a function of t, right? So we've done this before earlier on in multivariable. Now we're going to do it again, right? And we're going to, basically then adjoin to it our ds, accumulate all those together, and we end up with the value for the line integral. So one thing for us to note is that the value of the line integral is not going to actually depend upon the parametrization of the curve. And provided that we only have to move over the curve once as t increases from a to b. So as long as we're actually not moving backwards and forwards along the curve, okay, because you can imagine that what you're going to do if you move backwards and forwards on the curve, you're going to actually end up like subtracting out values for the integral. And then also, we also want to make sure that this curve is a smooth curve so that there's no bumps in it, or not bumps, but rather no holes in it, that we're actually looking at this something that's pretty continuous. Now, if we have those two things, then we actually have a lot of conditions that are going to allow us to, a lot of things that are going to look a lot like just working with regular integrals. For example, if I have two separate paths, right, and those paths are connected, and we don't move over those paths more than once, then what I can do is I can break up my line integral into those two separate paths, create integration for each one of them individually, and then end up with, something that, and then I can end up with the overall value for my integral. Excuse me. I can end up with the overall value for my integral. So let's consider this example. We want to evaluate the integral along a curve C, 3x ds, where it's two-parter. It's a two-parter. C1 is the parabola y equals x squared from 0, 0 to 1, 1. And C2 is the vertical line segment from 1, 1 to 1, 3. Okay? So what we're going to do is we're actually going to set up two line integrals here. We'll set up two line integrals. The first line integral is going to be for C1. So we're going to parametrize y equals x squared. So probably the easiest thing to do is just say, well, we'll let x equal t, and we'll let y equal then t squared. Okay? Since we're going from 0, 0 to 1, 1, that means that t is going to be less than or equal to 0, greater than or equal to 0 and less than or equal to 1. Our function then is going to be the integral from 0 to 1, okay? And then this is going to be 3t because x equals t. Now what I need to do in addition to that is I need to find ds. So my dx dt is equal to 1, and my dy dt is then going to equal 2t. So my ds is going to be the square root of 1 squared plus 2t squared dt. This is then going to equal then the integral from 0 to 1 of 3t times the square root of 1 plus 4t squared dt. And I will actually allow you guys to go in and you can integrate that yourself. What you should see here is that you're dealing with a trig substitution. Okay, so you're going to let t equal 1/4 tan theta. Yeah, 1/4 tan theta, that's right. Yeah, or 1/2 tan theta, excuse me. All right, next up we've got to do C2. So here was C1. Now C2, okay, it's a vertical line segment. So it's a vertical line segment, and so for that vertical line segment, notice that x equals 1. So that's consistent. X is going to equal 1, and y is then going to equal, well, y will equal t, right? Because we're going to have it's going to equal t, and then t is going to be greater than or equal to 0, less than or equal to 3. Notice, because y goes from 1 to 3, so t goes from, not 0, but from 1 to 3. Now we'll integrate. We got 1 to 3. Actually, before I do that, well, let's write this down. I'm going to integrate from 1 to 3. My function is now going to be 3x, so that means it's just going to be 3, because it's 3 times 1. And my ds is going to equal the square root of x of t, so that's 0 squared, because that's constant, plus 1 squared, okay, dt, and that just equals dt, right? Square root of 0 plus 1 is 1 dt, so it's going to be 3 dt. That one, you shouldn't have a problem with integrating either. So the line integral c of, in this case, 3x ds is going to equal c1 plus c2. We'll just add the two of them together, and that'll equal then the integral from 0 to 1 of 3t times the square root of 1 plus 4t squared dt plus the integral from 1 to 3 of 3 dt. And that's the entirety of our line integral. And that actually gives us one of the properties that we can use when working with line integrals. Kind of great. So a line integral is an integral. And so inevitably we want to think about integrals as areas. We might think about them as volumes. We want to think about them as like, we're accumulating something. And so that's got to be some kind of geometric interpretation. Well, there is for one. There is. So what we want to say is like, that in order to understand how it is that the area and the line integral are related, we should imagine our line integral in 3D space, okay? So we first take the curve C on the xy plane, and then we're going to project it onto the surface given by f of xy. So f of xy is something in 3D space, right? It's some curve or surface, or actually it's a surface, excuse me. It's a surface, and then we're going to take whatever we get on that surface, and we're going to basically project it down onto the xy plane. And that's going to give us something that looks kind of like a fence. All right, so like let's imagine that I've got the curve in space, okay? I've got, here's my XYZ plane, okay? My line integral is, let's say it's this thing right there, okay? So there's my line integral. And then let's say that my surface looks something like this, right? There's my surface. And so what I can do is I can imagine I can project that onto that surface. I'm going to get this line integral on the surface, whatever that looks like. It might actually be a bit more distorted. It's hard to kind of see there, but like that's kind of the idea. We project it onto the surface, and then we create something that looks like a fence, right? A two-dimensional object, right? And so if you kind of imagine, I'm drawing in my quasi-Riemann integrals, rectangles in there, that fence area, the area of the fence, is the value for the line integral. So that's the interpretation. For those of you who are very visual and you're like, hey, I kind of got it. Like, I want to understand what that means from an area perspective. That's what we're talking about. Take a simple example, okay? So let's just suppose, right, that C is the top half of the unit circle, okay? So we got C as the top half of the unit circle, okay? And f of xy just equals 2. So we got f of xy equals 2. So we want to imagine here's our surface, right? Okay. Here's the, so here's that top half of that unit circle right there. Right? There that is. Well, whatever. You get the idea. There's the top half of the unit circle. And then I've got the plane, right? Here's 1, z equals 1, z equals 2. So there's that plane. Okay. And what I imagine is that I kind of, I construct like this kind of, I construct a fence in between the xy plane and the plane z equals 2, and the area of this fence is going to end up being equal to the area of my line integral. Well, I can actually calculate that directly. So what I know is that the arc length here, since we're looking at the unit circle, the arc length here is pi, right? Because it's half of the unit circle. Whole unit circle is 2 pi. Half of it's pi, okay? Pi, and then its height is 2. So that area there is 2 pi. And what I expect is that for my line integral, right, that I should end up with 2 pi as well. And let's actually just check that. C is the top half of the unit circle, right? F of xy equals 2. So x of t equals cosine t. Y of t is going to equal sine t. We already know that ds, we saw this earlier, is the square root of negative sine t squared plus cosine t squared dt. And that just equals just dt, right? Because that's going to end up being 1. So we end up with the integral. Oh, and we've got to get that t is going to be less than or equal to 0, greater than or equal to 0, and less than or equal to pi. So our integral is going to go from 0 to pi, and it'll be 2, right, dt. This equals, I can do this one real fast. That's going to end up being 2t evaluated from 0 to pi, which just equals 2 pi. Ta-da! At least for that example it works. Now it works for all of the examples. This just happens to be one where we can actually draw the picture out. So from the perspective of area, we just have just a different definition of what it means to be the area, or a different way of thinking about area in this case. And integration, area, they still are connected. And they're connected with the line integral as well. All right, so now what we want to look at is we're going to change our notation up just a little bit. It's going to be very, very similar, and from a practical perspective, there's going to be really no difference. But sometimes thinking along the lines of our vectors, working with our vector formulations, is better conceptually. And in addition to it, it allows us to work with all that kind of like vector calculus that we saw in our very first chapter of this class, right? And so what we get when we work with that vector formulation is we're going to get the scalar line integral, or something called the scalar line integral. So to evaluate a scalar line integral, we're going to consider that f is a continuous function with a domain that includes the smooth curve C with a parametrization r of t, and that's a less than or equal to t less than or equal to b. Okay? So then our line integral, f ds, is going to be equal to, and so we've got r of t, my vector formulation, r of t equal to, and this is going to be the vector x of t, y of t, z of t, for example. Okay? Or we can use it as just x of t, y of t. Actually, why don't we start with that and then we'll move on. X of t, y of t, and then what you'll get then is you're going to get f of then x of t, y of t, right? Basically, that's what's going to happen when you plug that in, when you plug in r of t, so that's what that's going to be there, okay? And the magnitude of r prime of t, so the magnitude of r prime of t, right, is then just going to equal the square root of dx dt squared plus dy dt squared. And then you have the dt. So really, for all practical purposes, evaluating a line integral utilizing this notation is exactly the same, right? It's just that sometimes we want to kind of think about these from the perspective of a vector formulation, and that actually kind of sometimes ends up being kind of handy for us, and we'll see that in just a moment. Now, by the way, if what we do is we say that r of t now is equal to x of t, y of t, z of t, okay? So now we've got a three-dimensional vector for r of t, or a three-dimensional parametrization. Then again, we'll have f of x of t, y of t, z of t, okay? And then r prime of t, its magnitude, is then just going to equal that distance function again, okay? So it's going to be x prime with respect to x prime with respect to t, x prime of t squared plus y prime of t squared plus z prime of t squared. And then we just plug that in there, okay? So from a practical perspective, this is just allowing us to, like, you know, think about these things in terms of vectors. It also is going to allow us to do things like in more than 2 and 3 dimensions, right? Imagine parametrizations that are, you know, many variables. And yeah, so this is, and you're just going to see it. You're going to see it pretty often. So to make this rigorous, let f be a continuous function with a domain that includes a smooth curve C with parametrization r of t equals x of t, y of t, z of t, t greater than or equal to a, less than or equal to b. Then the line integral over c of f of x, y, z ds is going to equal a to b f of r of t times the square root of, like we said, x prime of t squared plus y prime of t squared plus z prime of t squared dt. Okay? And similarly, we can do that in 2 dimensions here as well. The integral of c f of x, y ds equals the integral from a to b of f of r of t times the square root of x prime of t squared plus y prime of t squared dt. Okay? And there you go. There's going to be our scalar line integral calculation, right? You should notice it's pretty much the same thing. So let's take a look at this example. We've got our line integral over the curve C of x squared plus y squared plus z ds where C is part of the helix parameterized by r of t equal to cosine t sine t, with t greater than or equal to 0 and less than or equal to 2 pi. So now what we want to do is we want to say, okay, well, here's my r of t, and so I know that this integral right here is going to equal the integral from a to b, okay, of f of r of t, right, times the square root of x prime squared plus y prime squared plus z prime squared. All of those are functions of t in this case, and then dt. So I'm going to first find x prime of t. That's going to be my cosine t. So x prime of t is going to then equal negative sine t. Y prime of t is going to equal cosine t. And z prime of t is going to equal 1. So my ds now is going to be the square root of negative sine t squared plus cosine t squared plus 1 squared. And this just equals the square root of 1 plus 1, okay? And this will be dt, so that's ds. And that's just the square root of 2 dt. Okay? So now I can just plug in my cosine, my sine, my t. But let's do that and then simplify first. So f of xy, xyz, or excuse me, f of t in this case is going to equal cosine squared t plus sine squared t plus t, which is just equal to 1 plus t. Okay, because this is going to equal 1. So now I put my integral together. I got the integral from 0 to 2 pi, right? Because that's given by my t's. 0 to 2 pi, I've got 1 plus t times the square root of 2 dt. And since that is actually fairly simple to integrate, we got the square root of 2, integral from 0 to 2 pi, right? 1 plus t dt. This ends up equaling root 2 times t plus t squared over 2, evaluated from 0 to 2 pi. And so what we get is root 2 times 2 pi plus, and this is going to end up being 4 pi squared over 2, so it's 2 pi squared. All right, so what do we do, right? We basically just said, okay, so that's my parametrization, right? Cosine t, sine t, t, right? I went out, I found my ds, right, by basically, finding that arc length, using the arc length formula, negative sine t, cosine t, and 1, okay? Simplified that, went in, and then figured out what f of r of t is by plugging in the value for my parametrization into the function, okay? And then my integration was actually fairly simple. Now we want to talk about just calculating arc length. And so just like what we've done before in our work, we always want to kind of like come back and connect things together, right? Okay, connect things together that we've seen before, see how things kind of like work together. And one of the things that I love about math is how consistent mathematics is in terms of, if you get like conceptually how something works and you kind of move into an area that's kind of adjacent with it, it should have some similar, it should be pretty similar with just some basic tweaks. So let's think about calculating arc length. And arc length is a basic unit of measure, right? Like volume, like area, okay? So we know that, like, say for example, area, we learned that area was equal to the double integral, okay, over some region R of, and this would be 1 and then dA, okay? And dA, it depended on how you went out and you parameterized your double integral. Like if we did polar, dA would be r dr d theta. If it was in rectangular, it was like dy dx or dx dy. But still, that's the idea. It was just 1, and that represented the fact that we didn't have any kind of like function, right, that we were evaluating over whatever area we were looking at. So it was 1 dA. Now, when we looked at volume, we could figure out that we could actually find volume using a triple integral, and that would be the triple integral over some region D, or we could call it over some volume D, over volume B, over some region D of 1 dV, where dV was, dependent upon the parametrization as well. Well, here's arc length, okay? And so arc length is going to be the integral over the curve that we're looking at, C, 1 ds. Okay? So basically these basic units of measure, area, volume, arc length, we can imagine them being the, in the case of arc length, since it's a one-dimensional figure, right? 1D figure here, that it's going to be the single integral over whatever curve that we parametrized of 1 ds. Our area, which is two-dimensional, two-dimensional, is going to be a double integral of 1 dA, and our volume, which is three-dimensional, is going to be the triple integral of 1 dV. Okay? And so when we're thinking about like, oh, hey, look, they connect. They work together. They're kind of consistent. I love that. I think that's really cool. In addition to that, this actually kind of sets up how it is that we find arc length when we're dealing with like scalar line integrals or vector calculations. Okay, and we can imagine that this is pretty straightforward, right? So like, let's say for example, we have a wire, and it's shaped like the parametrization r of t equals cosine t sine t 2/3 t to the 3/2, and we're going to take t greater than or equal to 0, less than or equal to 4 pi. All right, we're going to find its arc length. Notice we don't have any function because it's just going to be 1 ds, so we just need to figure out what ds is. So ds is going to equal the square root. We'll take x prime of t, so that's going to be negative sine t squared, plus, and then this is going to be cosine t squared, plus, and then the integral of 2/3 t to the 3/2 is going to end up being 3/2 times 2/3, right? It's 3/2 times 2/3 times t to the 1/2. So this is going to be t to the 1/2 squared dt. So my line integral, the integral is going to go from 0 to 4 pi, okay? And then my ds is just going to be, this is going to end up being equal to the square root of, this is 1 plus t, so it's going to be 1 plus t. The square root of 1 plus t. So root 1 plus t dt. And I will let you go through and integrate that. By the way, here's a hint, it's a u substitution. So you can go ahead and do that, okay? There it is. That's how we actually calculate arc length when we're going in and using the line integral. So this completes part 1 of our work with line integrals. We're going to start out with, first what you want to do is you want to go through and you want to parametrize the curve C. Okay? In terms of x, y, and z, x and y, whatever. W, x, y, z, whatever. Okay? Then find the value for ds, which is basically, right, it's that ds that you saw in Calc 2. Right, or your second semester calculus course, or essentially it's just going to be that distance formula where instead of values for x and y and z, we just plug in the derivatives. Okay, then we'll substitute our parametrization into the function f. Then we just go through, simplify, and integrate, and that pretty much explains what we're doing here with scalar line integrals.